you guys have forgotten just as much as the people that have taken OChem 1 really a year ago. And so what I want to do with this first session is really pull together all of the aspects of OChem 1 that I feel are important when it comes to the reactivity section, and filter and focus your efforts on what is important from OChem 1 and how can we apply it to what we're going to do. And most importantly, I want to say, here is the framework that we are going to use to examine reactions in OChem 2. Here's the framework that we're going to use to take a look at every single chemical reaction, and we're going to ask the exact same questions about each and every single chemical reaction. We're going to have the exact same tools to use to analyze those chemical reactions. And if we have these tools at our skill set, then we can deploy them and look at every single chemical reaction that we need to. And so I'm going to introduce these ways of looking at chemical reactions. I'm going to take a look at how we analyze those chemical reactions, and then I'm going to apply it to OChem 1 and tell you how do we pull from that stuff from OChem 1 and use these tools to analyze OChem 1. And then we'll take a break, and then we'll jump into the material for OChem 2. And so in order to do this, we are going to use my fancy overhead image capture thing that I got from the department when we left in the spring. So I'll jet over to that. Right now, if you have your colored pens, you'll want to get those out too, because we're going to start our conversation there with that little tiny video that I shared with you about how we're going to color code things and how those representations can be helpful. So taking a look at the docket for today and sharing this document visualizer. Hopefully you're looking at what would be the chalkboard in our class, and it's now a piece of paper on my desk that we'll be using. The first thing I want to talk about is representing chemical reactivity. Now, some of you may want to just sit back. Some of you might just have woken up. But some of you may just want to sit back and relax and watch the video and not actively participate, and that's just fine. Some people may just like to absorb what I'm saying right now. That's great. If you want to follow along with notes, that's great. But the beauty that I have found about teaching online and recording videos instead is the notes are right here. You don't see me. I'm pointing to the paper right here. I got to get used to this. The notes are going to be right here on this video all the time. And so what you choose to capture as you write these notes is totally up to you, but you'll have a permanent record as well. And I think that's really, really nice, a nice artifact of doing it this way. And so let's take a look. Oh, brand new pen. Representing chemical reactions. And so this is just typical note fashion, and I'm going to incorporate the color coding as we go along. So your primary notes are going to appear in black, and then any supplementary things that I find might be important for you to remember with respect to these notes, I'm gonna keep track of as well. And right here, this is the letter A. Believe it or not, it looks like a 2. It could look like something else completely. I just write my A's that way. I think contextually you'll figure out if it's a 2 or an A, but just be aware that that letter is in fact an A. You'll get used to it as we start along. When we look at chemical reactions, then there are 3 different ways that we are going to look at chemical reactions. The first way that we will look at a chemical reaction is when we take a look at its reaction scheme. And the reaction scheme is our shorthand. We're not going to keep track of absolutely every little tidbit of information in our reaction scheme. This is our what are the reactants? What are the reagents? And what is the product or products formed? And so this is our shorthand for the chemical reaction. And just for this, just as an example, we will take, it's already happening, OChem, six-membered ring. Uh, we will be taking just an example here of some halogenated organic molecule, and just say that it's reacting with methanol to form some type of product. And for this example, when I extrapolate this to some of these other pieces of representation of chemical reactions, um, we will be looking at what happens in its substitution reaction to form this carbocation rearranged ether. And if you don't remember everything that I just said as a chemical reaction, don't worry. That's kind of the whole point of this. If we are going to represent any chemical reaction that you need to memorize for this course or that you'll encounter in this course, which is probably a couple hundred, um, this is kind of what it's going to look like. At times, you're going to see reactions that you don't know what the products are. You don't know what the behavior is. And so, if you don't remember this from class, let's take a look then at how we can use these tools and these representations to help us. Let's take a look at then some color coding and what how this can become useful to us. Um, this species right here above the arrow. That species above the arrow, if we were to give, when we look at a chemical reaction, the behavior of the species that are involved, then we would accept that this species above the arrow here has two lone pairs of electrons on that oxygen, and that makes this species negatively charged. And we will call this, whoa, D, we will call this a nucleophile. Apparently, remember when I told you I was failing Latin at St. Olaf College? Apparently, this nucleophile comes from Greek, phile meaning loving, and nucleus being the other part of that word. And so you're looking at a species that loves something that is positively charged or has a nucleus that is positively charged, and therefore, if you love something positively charged, you therefore must be negatively charged, and we will call that a nucleophile. And you'll see that I will draw arrows to species in these notes that denote this as a nucleophile, and I'll always be using this light blue to do so. And so hopefully you have a light blue pen when you go back through your notes and can identify that as well. You don't need it right now. But that color coding, what I do in class and what I've had feedback from students is just having that same color all the time helps drive home that point. You must absolutely understand the simple definition of what a nucleophile is if you're going to be successful in this class. And it's just something that's negatively charged. That's it. We're going to encounter this together in class where we have these scientific definitions that were invented by some very hoity-toity people that have all, as you can see, aspects of Greek in them, because we want to make organic chemistry easier by making words that have Greek in them. But at its heart, we will together as a class get back to these very simple definitions. If something has a lone pair of electrons or a full-fledged negative, it will be a nucleophile. And that becomes really important because if we can identify a nucleophile, then all we have to identify is what the positively charged species is, and then put those things together. If then we are looking at a chemical reaction and its reaction scheme, then that reaction scheme is also going to capture the behavior of other species. It's going to have this kind of coded into it at its very nature. And so when we look at this species, hopefully you remember from Dr. Ramey's sultry southern voice that something like a halogen on a alkane, a hydrocarbon residue, that this species right here will behave as a leaving group. And for all practical purposes, a leaving group of a halogen, you're going to see that as a leaving group a lot in this class. There are other leaving groups that we'll see, like protonated oxygen, protonated nitrogen, but we'll get to that stuff later. I don't want to overwhelm you. But again, we can use color coding, and it doesn't pop right here as well as I'd like it to, but that is brown for a leaving group. And what's neat here is what this reaction scheme also captures is if we can identify the leaving group, then that means that in green here, I will be able to denote that there is unequal sharing of electrons in this bond right here, such that this chlorine has more of the electrons in this bond, and that makes this carbon electron deficient, that makes that carbon partially positive, and that makes this a partially positive charged species. One might even put partial positive like that, uh, and we would call this then an electrophile. And so this skill right here of being able to identify for the vast majority of reactions you'll encounter what is the negatively charged species, what is the positively charged species, and then what is the leaving group, I guess, is the impetus that drives the formation of the electrophile. That's really, really, really good for us, and that's all captured in our reaction scheme. And so what am I trying to do here in the morning? Well, I'm just trying to illustrate the key ways of analyzing a reaction and the tools that we have to do so. And this man, you're going to get really sick of me quick because I'm going to be taking this approach with every single reaction. And so hopefully this really regimented type systematic approach to every reaction will help you build the skill set that you need. And so why is this class important for medical school or something like that? Every time a patient that comes into your office, whether it's a human that can speak to you or a dog that can't, when they come into your office and they're sick, you have to have a systematic approach that allows you to navigate all of the possibilities that are there. I'm going to give you a set of skills that you can use to navigate any chemical reaction. Well, if we can identify the reactions and their behaviors, everything above and below the arrow and the thing to the left of the arrow, all of those things have to, at some point in time, play a role in the reaction. Well, then let's also use the reaction scheme as a opportunity to analyze some of the products that are taking place. And so some things that we can analyze then when we look at, now we've identified the behavior of the species before and above and below the arrow. Well, then at this point in time on the right side over here, there's some artifacts that we can also derive from this reaction scheme. And you'll notice that the connectivity has changed. And what I mean by that is, look, where the leaving group was attached, it's not there anymore. And now we've formed a new carbon-oxygen bond as well. And then don't forget that because this is a more advanced collegiate class, we're also asking you to remember that, hey, there is an implicit hydrogen atom that was right here as well. And there's one right over here as well. And so now they're both right on this carbon atom. And so there's some movement of some bond formation and bond breakages that are happening here as well as this reaction takes place. This idea is regiochemistry. And so the idea being, if a chemical reaction is taking place, then what region of the molecule is it taking place? Is it taking place at the exact same region as the leaving group was before? Yes or no? Apparently not. And then if we've then identified where on the molecule the chemical change is taking place, then the next question that we have to be aware of is if sp3 then, and then if I really had my game on, I'd cue the Darth Vader Imperial March music. But if we have an sp3 hybridized carbon, then we have to check for chirality. Ugh. Good thing here, I won't be asking you to identify R and S. We won't be really using those tools all that much, but we still have to ask the question of, if we form a new carbon nucleophile bond, uh, then when that bond forms, is it forming in the right-handed or left-handed version of the molecule, or is it even possible? And so the idea here that we're asking is stereochemistry of the product. And so the idea here being that look at how much information we can pull from our reactions when we look at this. We can identify from our reaction scheme the behavior of each reactant and species, and then we can also use that to identify the regiochemistry, and then the stereochemistry as well. What is the configuration of that bond that is formed? And so these are the fundamental questions that we'll be asking about every single reaction that we encounter, which is one, or A, the behavior of each species, and then B, the region and configuration of the bonds formed. Not bad for the first set of notes in a few months. And so that's the idea with the reaction scheme. And so just to extrapolate this just a little bit more, since we'll be running with this idea, when we look at a reaction scheme, the stuff above the arrow is typically the reactants that are involved. Typically below this, you'll see the solvent that is used. And I'll just insult your intelligence here. Products are going to be on the right, reactants on the left. And so you will see this type of thing as a representation of a reaction scheme. And you've probably seen these pretty simplified initially. Things will get a little bit more complex because sometimes you will also see now reactants, and we'll see this today, where you'll have reactants preceded by a number 1 and then solvent. And then you'll have another set of conditions and more solvent to make some type of product. Here, this is absolutely a two-step reaction. And so these numbers, the numbers matter. Don't forget them. So if you see a 1 and a 2, what that really is implying is that a reaction took place, and then you recovered some product and then had another sequential reaction take place after that. And the idea here that I just to show you is 1 OH minus 2 H3O plus means that you're taking base and reacting it with a species first. And after that reaction has taken place, then you're adding acid to that reaction. Okay, and the idea here is this is how you transesterify cooking oil into biodiesel fuel. You'll first add base, and after that reaction is done, then you'll add acid. That is completely different than adding this without the ones and twos. And I asked for someone in the class to tell me what this is, but we don't really have that set up. OH minus plus H3O plus, that just makes water. And so this is fundamentally just water, and water will never react with an organic species. And so at this point in time, don't forget that the numbers matter. 1 and 2 means two different reactions. If you forget the 1 and 2, it just means these things are combined at the same time. Just to rest the case here, just remember, if you accidentally do this on the exam when you needed the 1s and 2s, it's only going to be a half point off, and it won't kill you there. So just know this is important. And so another way that you will see this right here written then is sometimes you could extrapolate this to reactant, solvent, and then see this written again. Make a product. And so you might see that from time to time as well. So just know that these different representations and the different behaviors of these molecules are going to follow. Typically, the last thing is going to behave as a solvent, or the thing underneath the arrow will behave as a solvent. Don't have any solvent here. It's a solvolysis reaction, actually. The methanol is the nucleophile and the solvent. But that's for not here or now. So number 1, reaction scheme. We talked about how we can represent a reaction scheme or a reaction using a reaction scheme. Then number 2, letter number 2. Got to find a way to stabilize this by next class. Reaction mechanism. And so what is the reaction mechanism? And I can feel the vibe right now that some of you are having some PTSD type experiences when you hear that phrase. What is a reaction mechanism? It follows bond formation and breakage. Again, this is one of those moments that that we could get on one of these really hoity-toity definitions of what is a reaction mechanism, but let's just simplify together. We've got 5 weeks together. Let's not get lost in the minutia. A reaction mechanism is really simple. It's just a way for us crazy organic chemists to keep track of where the hell the electrons went. If I'm going to tell you that this reaction can take place, that's so much easier than moving a chalkboard around, then how did we make all those bonds that were formed and those bonds that were broken? How did we make that chemical change occur? And so if we're looking for that, then I have to be able to keep track of where the bonds formed and where they were broken. So I keep track of this at a fundamental level. Why is this even important to look at? It's really simple. Every bond formed and every bond broken either uses or requires energy. And because of some law I learned in physics once about conservation of energy or something like that, in order for these reactions to happen, we have to keep track of the energy required for them to take place. And so that energy is through the bond formations and breakages. And so that's why we're keeping track of this stuff. Let's take a look at the example then and how we can use reaction mechanisms to keep track of the flow of electrons. And I'm just realizing now, 26 minutes in, when I'm doing this screen, I don't need to be hand wavy because you can't see me yet. But what I would be doing right now is hand waving and showing you that of all the reactions that you will have to learn from my class, 80% of these reactions are going to be understood using a reaction mechanism. And so understanding this tool becomes really useful in explaining reactions. And the analogy that I would like to make when we're taking a look at reaction mechanisms is simple. You could memorize every reaction for this class, and you might find yourself doing that for the vast majority of them. Uh, but memorizing every reaction in this class is akin to memorizing your multiplication tables. And at some point in time, you did not memorize what 1,732 times 324.7 is. You learned a process by which to solve that problem. And so then you applied that process to any sort of multiplication process that or problem you encountered. Well, the multiplication table, that's all of these reactions that you have to memorize. And if you take a look at trying to memorize them, well, maybe you could make it a lot easier if you had a process, which is the reaction mechanism. And hopefully we can use these to help you categorize the vast majority of your reactions and work through them. Taking a look from the previous sample reaction, where we have this phenyl ring. A benzene is C6H6. If you attach a benzene ring to one other species, it becomes a phenyl, PHENYL ring. And here we have this phenyl where I had, I believe, a chlorine attached, and we were reacting it with methanol to make, and we're just looking at the substitution product that could potentially occur here. And we are going to write OCH3 plus enantiomer. Because of our previous discussion, the best and most important parts of these products, we now acknowledge we have to talk about the region of the molecule that it has to take place on. And then once we've identified where that bond is formed, we have to acknowledge, could stereochemistry play a role? And the answer is yes. This carbon is in fact chiral, but we don't have to do the RNS configuration here. We just have to simply acknowledge that we understand two products would be formed. Now, let's, taking that as our reaction example, let's look at this with the mechanism. So redrawing that same species with our leaving group, halogen, right here. And then in the presence of methanol, we want to be able to determine what type of interaction could take place in this reaction. Now, we could easily, we've identified this species right here previously as a leaving group. And because the chemistry is not occurring at the same carbon, we know that this is likely going to be some type of SN1 process. We have a secondary carbon or halogen right here. And we know already from the answer that we have a carbocation rearrangement. The regiochemistry has changed. And so it is likely then that we will feature some sort of loss of leaving group before we interact with the methanol. And so for us, we will draw an arrow like this, and it's a two-headed arrow because both electrons participated in that loss of leaving group, and we have broken that bond, showing that that bond breaks to the more electronegative atom. So let's supplement this with some notes. This right here, two barbs on the arrow. The arrow means two electrons traveled. So both those two electrons, they came from this bond right here and they traveled to that halogen. This is more electronegative. So the bond breaks toward this chlorine. leaving behind that carbocation. Hopefully, some of this is a refresher from something you've seen before. And then you'll see that step, then we can also name this loss of leaving group. So we've been able to keep track of where the electrons had to go in order for us to lose our halogen atom. And this type of mechanistic step is called a loss of leaving group. And I'm not going to spoil everything for you here, but as we work through mechanisms together, you're going to find that every single mechanism is just simply a combination of really one or two, well, actually 3 or 4 different mechanistic steps. So they're just like 5 Legos that you have to piece together. Once we have this species, we now have to account for the fact that the regiochemistry is changing. And so here, we can denote the travel of these 2 electrons and the hydrogen with it to form a new carbon-hydrogen bond and place our carbocation now at the more stable benzyl stabilized and tertiary position right here. Why that happens, it's not obvious, and we're going to need another tool to explain that, and that's something we're going to take a look at with our reaction coordinate diagrams in just a minute. But again, we can denote the travel of the 2 electrons and hitching a ride as this proton, freeloader, it's kind of like my 5-year-old, and put a hydrogen now on this carbon, which opens up this position right over here. This is a hydride shift. Shift, and a hydride is an H minus. Remember that as your definition. A hydrogen is an H plus. And so looking at this travel then of this bond as it breaks to form this new carbon hydrogen bond, now this becomes very obvious. We've already talked about this. Now we have an electrophilic position right here. So that will behave as an electrophile. It's a full-fledged positive charge. And what we need to do is react that full-fledged positive charge with something that is negatively charged, or a nucleophile. We can denote what happened here to form the new oxygen-carbon bond, which is the travel of these 2 electrons from the negative to the positive, to denote that travel and the formation of that carbon-oxygen bond. At this point in time, we have now created an sp3 hybridized center. And so we have chirality that we must worry about. And that oxygen that is attached now has a full-fledged positive charge on it. And so it looks like the last thing we have to do in order to complete this reaction, before I move on though, let's just do this. We have to give this step a name. This step is nucleophilic attack. Now that A looks like a backwards C. You guys are all smart though, you can handle that. We have to remove that last proton to get to the final product. The species that we have left is a chloride anion. And so the final product that we will derive is this chiral ether plus its enantiomer. And we achieve that by abstracting the proton with the anion and taking those 2 electrons that were on that in that carbon hydrogen bond and returning them to the oxygen in this manner. Uh, Now, because we are using a hydrogen in this reaction, and we're using something that's negatively charged, because this negatively charged species reacts with this positively charged species right here, and that positively charged species is a hydrogen, we have now entered the world of Bronsted-Lowry chemistry, which makes this species a Bronsted-Lowry base because it will eventually have the proton in the end, which makes this species right over here a Bronsted-Lowry acid. It's the proton donor. I guess it's this whole species right in here, that oxygen. And so when we see those reactions, these are equilibrium reactions. They're dictated by chemical equilibrium. This is a Bronsted-Lowry acid-base reaction to form that product. And I wouldn't expect you to always know that that is in chemical equilibrium. I'll always just be telling you that. That's an advanced OChem or grad school level of understanding, but I will be doing that just so you always know that this is then in equilibrium. But now, here, we've reviewed again how we're going to represent structures or reactions in this class. And so we've got reaction scheme, we've got reaction mechanism, and I have about 7 minutes then to go through the next method of representing chemical reactivity, which would be
Dr. Shaw, I had a question for you.
Yeah.
So we would consider the last step of that mechanism a Bronsted-Lowry acid base rather than a proton transfer?
Same thing.
Okay. And then with just kind of figuring out whether that was an SN1 versus SN2, it makes more sense to look at the hydride shift than the fact that methyl hydroxide is a weak base and weak nucleophile, and just have that memorized.
You're asking a question about being able to identify no, that's not the word. The imperative word is predict. You're asking about the skill set of being able to predict what the products are from a substitution reaction or predict what the products are from an elimination reaction, and then going one step farther, being able to predict the pathway that separates those two, or E1 or E2. You do not need to predict products. You just have to, from E1, E2, SN1, SN2 type reactions, merely what you need to do is just identify that a substitution reaction has taken place. I will not be asking you to differentiate between substitution and elimination. I just need you to know that this example that we've been showing you, you're going to find in your notes that could also make an elimination product as well. But for our practical purposes, the way this was delivered, we have some key features that allow us to know a substitution has taken place, and that's as far as that's going to go. Just be able to recognize what a substitution reaction is, what an elimination reaction is, but the nuance of being able to predict, that's something that was for OChem 1, and we're not going to use too extensively for us.
Okay, awesome. Thank you.
Moving forward, and people, please just chime in like that if you do in fact have questions. I have so many things up on my screen, I couldn't possibly keep track of everybody. So if you just have a question, please just interrupt like that, and I'll be happy to answer them. And then we'll also be going over this stuff this evening with some more applications as well. The last thing I want to share with you then is, well, there's 3 ways to look at a reaction. The last one, reaction coordinate diagram. Why do we have this method? Well, if a reaction scheme is the shorthand, reaction mechanism allows us to keep track of the flow of electrons, which is crucial in identifying bonds formed and bonds broken. Then reaction coordinate diagram, it's all about energy. Energy drives the world. It drives our economy. It drives life, and energy. It drives chemical reactions, and so we have to be able to keep track of the energy that occurs as a consequence or as a requirement of any one of these chemical reactions. And in order to do that, we're using a reaction coordinate diagram. And this reaction coordinate diagram is drawn such that we keep a non-quantitative. Now, you can take physical organic chemistry and get all quantitative if you want to, but for us, we're just going to say qualitatively, potential energy is increasing on our y-axis as we move up, and then reaction progress is moving from left to right. And so the idea being is, as the reaction progresses, what are the energy consequences for that? And so when we look then at applying a reaction coordinate diagram to, and if I can just zoom out here, boom, to this reaction, then at the start of our reaction, we simply have this benzene ring that has that halogen on it, and it's sitting at some sort of energy. Then, as that reaction progresses, you'll notice that each and every single step in our reaction mechanism, so the transformation of this halogenated compound into its non-halogenated carbocation formed, well, when that takes place, there is an energy consequence for that. We want to be able to keep track of that. The species that has the carbocation is incredibly high in energy in comparison to the non-carbocation reactant. And so we are able to denote that as the reaction progresses from the thing with the leaving group to the thing that does not have the leaving group anymore, there is an energy consequence as we progress that way. And as the reaction needed to progress, it needs to pass through some type of transition state in order to achieve that carbocation state. And so moving forward, each and every single reaction step has an energy consequence. Each and every single bond breakage or bond formation has an energy consequence to it. Therefore, we have to be able to keep track of that energy in our reaction coordinate diagram. Moving that carbocation to a tertiary benzylic position is going to decrease the overall energy of that carbocation, acknowledging that the reaction would need to go through some transition state in order to achieve that. And if we were to just draw what a transition state for that might look like, for that one step, you might be asking a lot of myself here. We'll just see. You're looking at a hydrogen that's kind of partially bonded to this carbon and this carbon at the exact same time. That would be the transition state right there. Boom. Now we have the reaction of the alcoholic nucleophile with the electrophilic carbocation. That's going to form a new bond, and when it forms that new bond, that's an energy consequence that must take place, and so we now have a species that is no longer charged at the carbon. This is still charged right here, and so we likely have a more stable species here. And then at the very end, we completely decharge that molecule by removing that proton to leave our ether, which would be even more stable. And so we would be able to construct a reaction coordinate diagram for this hypothetical reaction that I proposed. Let's see, back to me, I guess. That's it for this section. We have talked about the three tools that we are going to analyze every single reaction that we encounter with. And so this is going to be a great video for you to revisit, because you are going to see me going through the same exact process with whatever reaction that I encounter, starting with addition reactions to alkenes when we get back from our conversation or from our break. I need some water. I need some coffee. We'll reconvene here at 10 o'clock. I'm just going to stop the video and mute. So go ahead, take a break, gather yourself, smoke something. We'll be back here in about 13 minutes. Today's Boone weather update for the 4th of July weekend, July 2nd. This is for all of you off the mountain. It is a balmy 70 degrees up here with a nice cool breeze. So if you're off the mountain and it's steaming hot and disgusting, your alma mater is up here chilling out. It's absolutely gorgeous and fantastic. My challenge for the day, my Tour de France challenge, has me going up and over the Blue Ridge Mountain on my bike, or Blue Ridge Parkway on my bicycle this weekend. So that will be absolutely gorgeous. Uh, Things are starting to pick up here in Boone. There's more and more people coming around, which is good. Which is good for the businesses around here. That's for sure. It's nice to see people out and about, being safe for the most part, except those Florida license plates. There's so many of them. I'm afraid they're going to hit me on my bicycle. But such is the risk. So come back. It's gorgeous up here. That is for sure. Moving on. If you have questions, please don't be afraid to just chime in. Just a few things of note logistically. I think the As You Learn page is all set and ready to go. And so you should be able to access all current resources there. As you noticed last night, the announcement section of the As You Learn page is what I use to communicate with everyone. And so you'll be getting a lot of messages through there. And then keep checking back to the video pages for my channel on YouTube, or the course channel on YouTube, rather. You'll find a lot of information there as videos get posted for you to devour. And so also note there's a forum there for any content questions on As You Learn. Please feel free to just, instead of emailing me, just post them on the As You Learn page. And I have it set so that I know when someone posts there. So any content questions, please feel free to post there, and I'll reply to everyone so that everyone is getting the same answers. Uh, um, and have access to the same answers. And then finally, the last thing I'd just like to mention is there were a few people that have some conflicts with the examination block period. If that's you, if you need to work, if you have anticipating missing that examination period, um, once or every time due to work, just reach out to me and let me know. We can certainly work around something as long as we can make sure you're taking it that Sunday. My hope and the reason why we're taking the exam from 10 o'clock to 2 o'clock is as soon as you submit those examinations at 2 o'clock, I am going to start grading the exams. And so if you have to make an exception to take that at a later time or earlier time on Sunday, that's just fine. Just know that you might not get your examination back that evening. You might just get it back the next day. I try and turn them around as fast as possible, but that's the reason for the block. So if you have a conflict, I know you got to make the money too. If you have to do that, please feel free to do that. I will work with you if we have to shift that block around as well. So just be aware of that. Moving forward, then we get to talk about our very first functional group. And so as you learn, there's a list of functional groups that you have to memorize, and that's because you have to understand the language that I'm talking and using. And the language that I'm going to use is alkenes. We are going to be talking about reactions of carbon-carbon double bonds, alkenes. And so when I say alkene, immediately in your mind, you need to think carbon-carbon double bond. And the whole point of this entire unit from here on to the first examination is talking about all the reactions of double bonds. And so how pervasive are double bonds? Well, they're also called olefins. And if you look at your clothes, if you're wearing any right now, or at least look at the carpet or bed sheets that you're on, those things are olefins. They're any sort of material that has a double bond. And so you're looking at like polyethylene or polypropylene. Those types of man-made fibers are carbon-carbon double bonds. They're called olefins. We'll be looking at their reactivity. And just to give you an idea of kind of how this class is going to progress, it's pretty much here's a functional group, carbon-carbon double bonds. Let's talk about how we make them, how they react. What do we do next? Move on to the next functional group. And for us in this unit, it will be carbon-carbon double bonds that are right next to each other. They're called conjugated double bonds. And so at that point in time, we'll be taking what we learned from carbon-carbon double bonds. Actually, we're going to do triple bonds next. Applying it to triple bonds, applying it to carbon-carbon double bonds that are conjugated, and then carbon-carbon double bonds that are aromatic. And all of those are going to fit together in one unit. And so we're looking at the reactions of carbon-carbon double bonds. So at this point in time, let's take a look at we're looking at how do we we're looking at the functional group of alkenes. And so the first thing that I want to do is take a look at saying um, how can we make carbon-carbon double bonds? And this will be a review of short for us from OChem 1. And so when we start by saying we are looking at alkenes, then the first thing that we're going to do is we are going to look at how those alkenes are synthesized. So synthesis of alkenes. And so we look at synthesis of alkenes, and the easiest way to remember that is we synthesize alkenes through elimination type reactions. And for us, then the chemical reaction scheme that we would use to describe elimination reactions would be generically, we'll stick with the six-membered ring here, having some sort of halogen, typically, or leaving group, we'll just stick with the halogen, and then some type of base and ultimately generating a double bond as a result. Yes, this species could also undergo some type of substitution reaction as well. And this kind of gets back to the question that was asked earlier. What do we need to memorize from this substitution elimination stuff from OChem 1? Well, the answer for that is just being able to identify that, yes, these species could have undergone a substitution reaction, but in this case, it's just an elimination. And so differentiating between substitution and elimination right now, not important. Acknowledging this as an elimination reaction, absolutely. And so if I told you we had tools that we use to look at chemical reactions, then let's apply these tools to this chemical reaction. We have some sort of leaving group right here. We have something that is going to behave as a Bronsted-Lowry base. Okay, I'm also going to write here, it could be a nucleophile. It absolutely could be a nucleophile. And it would make a substitution product. And so in this case, we're just looking at it behaving as a Bronsted-Lowry base. Both of these things are negatively charged. All nucleophiles are bases, but not all bases are nucleophiles. Yeah, we'll go through that again later. And then also acknowledging right here that there is an implicit hydrogen atom right here that we will need to eliminate to make that alkene. Alkene functionality. And so we're just going to examine this as the common E2 type reaction mechanism. So here's the scheme that we would have, and I always seem to leave this stuff off, but if we're keeping track of all of the atoms here, you would absolutely be making water as a product of this reaction, and you'd also have this Cl minus here, but we're usually only worried about the carbon substrate. So if that's the reaction scheme, we can look at this as a reaction mechanism as well. How do we synthesize alkenes? Well, starting with this halogen, and now that implicit hydrogen is explicit, we are looking at a simple E2 type reaction where the electrons on our base are used to abstract a proton. And so this is a Bronsted-Lowry acid-base reaction. It would be in equilibrium here. These electrons in our carbon-hydrogen bond are now used to form our new carbon-carbon bond, whilst we jettison that leaving group all at once. It's all concerted, and we end up forming this alkene as a result. The name of the game here would be a Bronsted-Lowry acid-base reaction or proton transfer. You'll hear me refer to both of those. As we get further and further in this class, I'm going to free you up to simply write this as minus H plus H. The idea being there's a removal of a proton. You could put it back on going the other way. You could probably denote this as a proton transfer here. That is something we'll get to in the future to be aware of. But this is just a simple Bronsted-Lowry acid-base reaction. We generate an alkene. And guess what? That's it. That's it for our review of, we could take a look at a reaction coordinate diagram, really not going to be used here because we don't need to explain. We'll use it to explain phenomena when necessary. But here's an example of, oh my God, I haven't had OChem in a long time. Now I need to regurgitate that OChem. Well, this is it. I'm not asking you to know the stereochemistry of the product here or anything like that. We're just simply saying, hey, look, here's the elimination reaction that we can use as a method of generating the functional group that we are interested in, this functional group being an alkene. And so here's our scheme. And here's our mechanism. So, when we start to look then at the reactions and how alkenes react, I want to point your attention um, to this, which is all the reactions that you need to know for these 10 different reactions that occur with alkenes. How do we, in fact, synthesize or react different alkenes? When subjected to different conditions, what types of reactions can this carbon-carbon double bond bear? And what I'm going to do is I'm going to make the case that the vast majority of these reactions fall into really two different categories. And so what I'm going to do is I'm first going to take all of this information right here, this pinwheel of death, and I'm going to tell you that yes, you do in fact need to memorize all of these reagents in some form. Many of you could use the reagents app that is referenced on As You Learn is a great application. Some of you, if you have access to the Wiley Plus, if you go to the Read, Study, Practice portion of the online text, there's a great fill in the blanks quiz at the end of the chapter that allows you to practice memorizing these reagents. Some of you will put these on note cards. Some of you will do what I do, which is the psychopath thing, which is I just write down the reaction 100 times on a piece of paper, because for me, seeing something isn't memorization, writing it down is. And so I force my hand to write it down 1,000,000 times to memorize it, because I'm a fool and it takes me that long. But you will have to memorize all of these reagents. But what I'm going to tell you is, of these 10 different reactions, 12 total different sets of reagents, 8 of these reactions can, or 7 of these reactions can all be put into one category that all follow the same exact mechanism. And so what I'd like to do first is take a look at an overview of this pinwheel of death in a much more organized fashion and filter and focus these into the ones that follow the same mechanism and the ones that you just need to memorize. And then what I'll do is I'll give you the tool that shares the mechanism that shares all of these same reactions together, so then you don't have to memorize them. You can just critically think through, and you'll see what I mean. Let's take a look. So stop sharing this and go back to the visualizer. So now we're moving on to alkenes, and then reactions of. And so you have this pinwheel of death. And if you want to, please go to As You Learn and pull up this document. It is under Reaction Webs. It's under Chapter 8, Addition Reactions, just to be looking at this. You'll be able to cross-reference this when you review the video as well. There are a number of reactions that alkene, that's methyl cyclohexane molecule, can potentially undergo as proposed in this pinwheel of death by your author. Of those 10 different reactions, they all follow under really the same different types of categories. And the first one is addition reactions. And I'm going to write mechanistically. Apparently, writing and speaking at the same time is a skill that must be practiced all the time. As you've noticed, every time I've opened my mouth whilst writing, I've had to stop. That's not always been the case, so hopefully I get that skill back. Mechanistically similar. What I mean by this is kind of our analogy to our multiplication table. And what I mean there is that we will have one mechanism that we can apply to all of the reactions that fill into this category here. And we can apply that same process to all these reactions, and you may not have to memorize them like you would some of the others. Then there are oxidation reactions. And these types of reactions are far and away outside of my realm of expertise. And more importantly, they're not mechanistically well understood. And so these are definitely Memorize. Now, I will, when I go over these reactions, absolutely give you some skills and some tips to help you remember some of these things. And there are absolute ways that we can envision these reactions. But because there's so many electrons flying around in solution, because these things are called oxidation reactions, the pathway by which these molecules form are not necessarily all the same. Well, if you have oxidations, then you also have reduction reactions. And here, this is a memorize as well, and there's only going to be one here. And the fun thing about this is if you remember the word reduction and then you remember the set of conditions that are required for that reduction to take place, it's going to be the same set of conditions for every reduction we encounter for this whole semester. And so there's a lot of overlap is what I'm trying to say. Last then but not least, a word that you've associated probably with politics recently with the radical far left. For us, we're talking about radical reactions, reactions that occur with a single electron. And these are mechanistically complex and something we may or may not get to. And so these reactions from this pinwheel of death will fall under the memorized category. Let's break these down. The reaction of something like HX, and this is the reaction that's called the hydrohalogenation, and this is being done Markovnikov addition. This right here is an addition reaction that will share the same mechanistic DNA as any other reactions that fall under this category. Number two, then, is the only radical reaction that you will encounter in this unit, which is the addition of HBr in the presence of peroxides. Not sure why I added another syllable there. This is reaction number two. And the benefit here is this is, again, a hydrohalogenation reaction, but you may remember this idea of Markovnikov, anti-Markovnikov, regiochemical products. That's something that we're going to see in this unit. You may have kind of heard of it from lab, perhaps. This is a way to vary the regiochemistry, and that's something we'll cover extensively. These work hand in hand. Then moving on, we can add water to a double bond. And so this would be taking a double bond and adding OH to it. And so this would be reaction number three, the addition of H3O plus. And so this is an acid catalyzed hydration of an alkene, and that adds a OH group to that alkene. Hopefully you're looking at that pinwheel. I wish I could cast both at the same time. There are two methods to accomplish with these. Both of them share the same mechanistic DNA. One uses mercuric acetate followed by water, and then treatment with sodium borohydride to add OH. And the other one is just to take acidulated water to add OH to a double bond. And so the idea there is, and just so why are we doing this stupid shit? Let's be honest here with this OChem. What practical purpose does it have? Well, let's just talk about stains for a second. If you spill something like spaghetti sauce on a carpet, everybody knows that that's probably going to leave a red stain. Well, what is carpet? Carpet is a polyolefinated compound. It's got a bunch of double bonds in it. And what is spaghetti sauce? Well, it's acidulated red juice. I mean, tomatoes are acidic. It's a red compound. And so you're adding some kind of acid and changing the chemical reactivity and covalently bonding some sort of red species from your tomato sauce to the double bond using one of these reactions. And so, yes, this has applications to it. And yes, you are absolutely screwed when that happens. And so it's because there's not irreversible covalent bonding forming between those olefins. And so it's just wild that way that there are applications to this. Moving forward then, if we look at number four, We're going to skip number 4 for just a second. It's a hydroboration oxidation reaction that adds an OH in the opposite regiochemistry. We'll come back and talk about that in just a second. But if we then move to 5, H2 over platinum. So very expensive reaction to conduct, but this is the reduction reaction. And so you just have to memorize that when you start with the double bond and you add H2 over platinum, you will no longer have a double bond. You've gone from an alkene to an alkane. Then moving on to number 5, adding or number 6, adding bromine, Br2. And this it doesn't say this, but chlorine 2 also works. 3, 4, 5, 6. Bromination, chlorination, they follow the same exact reaction mechanism as any of these other ones above it. And that's what I'm going to spend some time on after this, is talking about how that mechanism works and how it could be applied to all of these examples. Bromination in the presence of water, which is called halohydrin formation. And if you're looking, it's the product of 7. You have a halogen, halo, and you have a OH, so that should remind you of water, hydrin. See what I mean by these definitions? It's so stupid. You lose so many people by making this so complex. You've got a bromine, you got a damn halogen and an OH on the molecule. Apparently it's called a halohydrin. How do we form that? Well, it's the same mechanism here. And I'm going to show why this happens, even though it's the same mechanism as this, and this. This would be example number 7, I think. Yeah. And then last but not least, before we go back to the one we missed, you have some oxidation reactions that essentially add OH groups to this molecule. So you either have OHs adding to the same side or the opposite side. These are all oxidation reactions, and this would be the anti-dihydroxylation reaction 8 and the syn dihydroxylation reaction 9. Both of those reactions, all of those reactions, as well as 10, which is the ozonolysis reaction, O3, can all be thought of as some type of oxidation reaction, and these all fall into the memorization category. I will give you some very great hints on how these reactions work and give you some ways to think about them, but they don't share the same mechanism. And so let's just walk through these and get them in our notes. This peroxy acid, which would be any carbon residue that is attached to a double bonded O, and then another oxygen. This is a peroxy acid molecule, 3 oxygens in a row. That's not a typo. Followed by acidulated water. This right here is an oxidation reaction. It will add 2 OHs to the reaction. And that would be number 8. This also works for the addition of potassium permanganate in the presence of basic conditions and making sure that thing is cold. Or this can also be achieved using osmium tetraoxide first, and then following that by the sodium sulfate in water. Both of these reactions add 2 OH groups to the molecule on the same side of the molecule. We'll come back to this and review it in just a little while, but those would fall under our oxidation reactions. And then finally, this O3 thing. This reaction is really cool, DMS. Using ozone, followed by dimethyl sulfide, you can actually split the double bond in half. And we'll come back and talk about that as well. But that reaction falls under the oxidation set. And then finally, the last thing we avoided and are coming back to is letter number 4, right here, which is this addition of this, followed by NaOH and peroxide. This reaction, the first half of this shares mechanistic DNA with the addition reactions, and then the second half of this reaction shares mechanistic similarities to the oxidation portion. And so we'll be able to track at least the top half of this reaction with the same type of mechanism as well. My hope here is that these all seem similar to you at the end of this conversation, this one-way conversation, that these all fall into the same class, and you can rationalize these. And then probably on Monday, we'll talk about how to think about these in a real nice, easy way. And the great thing about this, if we may just jump out of this for just a second, and I want to try and show you where we're going with this course or this unit, and then also share with you how you're not, the work you're doing here is going to be important for you. Let me go to this section right here. You're also going to have to look at alkyne reactions. What kind of reactions? All kinds of reactions. It's gold. All of these reactions that you'll also have to learn for this next unit, you will find that all of these reactions here are actually the same as these reactions. You're just using double bonds here and triple bonds here. And so just know that, yes, this looks like I've got to memorize so much between these two. There's a lot of similarity between those two. In fact, they're just the same reaction twice. With that being said, are there any questions, or people want to jump in with any questions you have right now? We've talked about the tiny little bit of stuff that we have to remember from OChem 1 as far as just how do we make an alkene, and that's an E2 reaction with an alkyl halide and a base. And then we've slowly started to take this pinwheel of crap that we have to learn for alkenes and hopefully filtered them into some simple categories here that help you delineate which ones you can memorize and which ones will share some mechanistic similarities. So moving forward then, and if you have a question, please just jump in. I want to talk about this right here, which is the mechanism that these reactions share. And just a reminder before we jump into this, I will be on tonight at 8:30, I think I said, and I'll have some practice problems that I'll be going over this. It will not be a tie event, so that'll be that'll be a chance for you to really ask questions about what's going on too. So please tune in there and feel free to join me while we go over applications of this. Yes, absolutely. The autofocus on this thing, the question that was asked is, can we get a copy of these notes? I'm going to upload these notes immediately after this online as an accompaniment to the video as well. So you'll have those, and that way you can, it's much higher fidelity, so you can be working on those and have those at your disposal. The mechanism that these all share, and I'm pointing to the paper here, you can't see that, but let's take a look at the mechanism that all of these things do in fact share. So again, reaction mechanism for all of these. And I think when we join together on Monday, I'm getting a bunch of AV stuff that'll allow us to have a different format here that'll be a little bit cleaner for everybody. So we have that to look forward to as well. But the idea being here is these things, and when we move to even triple bonds, these same reactants are going to behave in a similar fashion with triple bonds. So let's take a look then at that similar mechanism for addition reactions. So alkenes, and then we'll say mechanism for addition reactions. If we were to take an alkene and we were to react it with some species, and for this I'll just use the example of HX, then we are going to eventually synthesize the addition of that halogen and hydrogen to that double bond. And the idea being here that when we look at these other reactions, the hydrogen being added is the one from this H3O plus, and then the other thing that could be added would be the OH from here. Br is going to behave in a similar fashion as well, that there will be some sort of reaction that occurs with our double bond and the species up here to make something like this. So if that's the case, we've already given you the tools by which we're going to look at every single reaction, so let's apply them. And so let's first do our behavioral analysis per se of the species that are present, and then we'll do our product analysis, the regio and stereochemical product of this reaction, and then we'll talk about its mechanism and how it could be applied to really any of these reactions. Behavioral analysis says when looking at our carbon-bearing residue with our olefin, this carbon-carbon bond, that thing has electrons between those two bonds. This is electron rich, and therefore, if that electron-rich thing is going to love something else in a very binary fashion, then it is going to love something that is electron-poor, and that's going to make it want a nucleus, or nuclei, in my mind, which is positively charged. And so we are looking at calling that an nucleophile. Behavioral analysis says then we have to identify what the heck the behavior of this species is up here. Anytime you see a hydrogen atom that is acidic, and so in this case you have a strong acid in HX, maybe HCl, HF, HBr, those acids donate a proton, so that H is actually a plus, H plus almost. And so if we have an H plus, it's going to love something that is electron rich in a binary fashion, and therefore we are going to call that an electrophile. It will want to react with something that is negatively charged. If that's the case, then the behavior of this initially is as a leaving group. It's going to leave the electrophilic hydrogen and break that hydrogen halogen bond in a manner that the hydrogen and the halogen does not break that bond evenly, does not break it homolytically, and both of those electrons go to the more electronegative halogen. Well, if that's the case, we've identified the behavior of the reactants in this reaction, then we have to analyze the product and ask ourselves the question of what region did the reaction take place on? And if we want to get really fancy, we'll call this regiochemistry. But what region of the dang molecule did the chemistry take place on? And I have carbons 1 and 2 just arbitrarily labeled right there. And I can see the claim now. That's hard to see, but you will in the notes. This same 1 and 2 carbons are where we've added the proton and the halogen at the end. And so the region is the same. The regiochemistry is taking place on the same atoms that were occupied by our functional group, which are these right here. But you should note some things to note, that the hydrogen atom went on the carbon, and in this case I have it labeled carbon 2, which has more hydrogen atoms on it. Question mark, dot, 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 trailing off. Let's see if that's true. There is one implicit hydrogen here. There are no zero implicit hydrogen atoms here. Now on this carbon atom, we have two implicit, well, one implicit, one explicit, for a total of two hydrogen atoms here and zero here. So when we're looking at adding a hydrogen to this molecule, the hydrogen seems to be adding to the one that already has the hydrogen. And so that was the longest winded way of essentially saying, this is Markovnikov, M-A-R-K-O-V, Markovnikov addition. You are likely to find that spelled differently. But you are adding, there's a law, a rule that the thing with the protons gets the proton. That's called Markovnikov addition. I'm going to add a proton because it is the electrophile, and when it reacts with this nucleophile, that proton could add to this one carbon. It could add to the two. Markovnikov is suggesting that when given the choice, the proton is going to add to the thing that already has the proton. And then stereochemistry. Oh, God, stereochemistry. In this example, neither carbon atom, and that's one or two, is chiral. Thank God. And so at this point in time, we don't have a chiral center at carbon 1. We don't have a chiral center at chiral 2. And so we don't have to worry about stereochemistry in this example. But stereochem could be a consideration in other examples. And that's, I guess, the idea is saying once we apply these tools to this reaction and we've added something to the molecule, we formed new bonds, we've broken that that carbon double bond, then we have to ask what is the configuration, because each of these dang things is tetrahedral. Well, it turns out neither one of these carbon are chiral, and so we don't have to worry about stereochemistry. But if you did form a chiral center, yes, you would have to worry about it. And you'll see examples of that this evening. So again, this is how this is how class is going to be. Look at a set of reactions, try and filter and focus them into similarities, then try and tie those similarities together. And the tools by which I'm going to prove to you those similarities exist are taking a look at the reaction and doing its behavioral analysis right here, and then careful analysis of the products. And then once we've done that, we can make a case for how these reactions are going to proceed and hopefully apply the similarities to all of these reactions that are addition reactions. So let's take a look at the overall generic mechanism that would occur when we reacted this methyl cyclopentene ring with HX. We've already said that this species right here will behave as our nucleophile. We've already stated that this species right here will behave as our electrophile. And then as a result, something's got to leave. That's this right here. If you can do this by just identifying the behaviors, then the reaction becomes really quite simple. Ochem is no more than simply finding the negatively charged thing and reacting it with the positively charged thing, and then looking at the consequence of that happening. the vast majority of reactions that are not oxidation, that are not reduction reactions, they all follow the same premise. It's got to be a nucleophile reacting with an electrophile. And if I can figure out what the negative thing is, then I can figure out the positive thing. Then the mechanism is merely the reaction of those electrons with that hydrogen to break, and the consequence is the loss of that leaving group. And we are going to put the proton on the carbon that already had the proton, leaving behind a carbocation in the more stable tertiary position than if we would have added the hydrogen here and had the carbocation here. The more stable carbocation, that's why the hydrogen adds to the one with the implicit hydrogen. That's Markovnikov addition right there. We get that through some type of nucleophilic attack type step. Not sure why I did that. Well, then once that's taken place, we have a halogen anion in present in our reaction mechanism, and all we have to do is take a quick check of the behavior of these species. Well, if this reaction is purely governed by plus charges and negative charges reacting with one another, if it's merely a love story and our protagonist is this nucleophile and it has to find this electrophile, and that's our entire Disney love story right there, well then, hey, here's a positively charged species. I'll call that the electrophile. Here's a negatively charged species. I'll call that the nucleophile. Nucleophilic attack of that nucleophile at that carbon center. That is how we end up forming that halogenated alkane as a result of that alkene reacted with HCl. So why is it bad for you to get HCl on your skin? Well, your skin has a lot of double bonds in it, believe it or not. And so you mix HX with that and boom, you start reacting and adding halogens to your skin. Yay. And so that is the chemical mechanism here. This would be just another nucleophilic attack step that is used to generate that product right there. So let me just jump. Does anybody have any questions before I jump into the similarity aspect of this? Please go ahead and unmute yourself if not. What I want to do is essentially show you then how this is similar for a lot of these other reactions. And then this evening we'll go over some examples of these reactions, and then we'll continue to pick up with these other ones when we get together again on Monday. If you don't have questions, let me show you then how this is very similar to other reactions that are in this list. I want to prove to you that if it works for HX and it's an addition reaction, then H3O should behave in a very similar fashion because it is the same type of reaction and it shares mechanistic DNA. Same exact alkene reacting with HOH2. So that's just H3O plus written in a more explicit way. Huh. I did the hard work. If we're doing behavioral analysis, if it was a nucleophile before, it's going to be a nucleophile again. And that is actually a common misconception that I made. Is when I took this class, I kept thinking to myself, man, all of these reactions are different, and it's not true. They have similarities. Any double bond is always going to behave as a nucleophile. So if that's the case, then when I look at all of these reactions, I really just got to figure out what the heck the electrophile is. Hey, It's the plus of the H3O plus. And if that's the case, then the mechanism should be similar, where I abstract a proton, the bond breaks, I've added the proton to the one that already has the proton, leaving behind the carbocation on the more stable carbon of the two. And all I have left is water. Well, I'll do the hard work. If it was an electrophile before, if a carbocation, which is deficient of negative charge, it is a full-fledged positive. If that sucker was to react, it would want to react with something that's negatively charged. I've got a water molecule that is somewhat negatively charged. It's got 2 lone pairs on it. Not your best nucleophile, not as good as this one, but it's still a decent nucleophile that we could react that nucleophile at that electrophilic center. And look, by following the exact same mechanistic pathway, I have now added a water molecule where I had just simply added a halogen before. Same exact reaction mechanism. And just to note that all we need to do is deprotonate that species to be left with the hydrogen portion of the molecule, not the protonated part. And this would be our Bronsted-Lowry acid-base type step. And yes, that is in equilibrium. So if I'm making the case that this is true for HX and H3O plus, let me do one last thing before we conclude, which is do the exact same example in the presence of diatomic bromine. Let's take a look. Behavioral analysis says this should behave as a nucleophile. I don't necessarily see an electrophile right here. If we were to simply say that there were van der Waals interactions, if we just acknowledge that nothing is freaking static at all, and a bond is dynamic, and these electrons are over here every once in a while, and over here every once in a while, and then back over here, and then back over here. Well, when the electrons are over here, that makes this partially positive. And if the electrons sit back over here, that makes this partially positive. So in the absence of absolute zero, the electrons are moving back and forth between these two halogen atoms. And in doing so, it creates a deficiency of electrons on one side, partial positive, and a partial negative over here. That's going to be good enough for an electrophilic position. And what happens is we see this nucleophile adding to that electrophile right here. Things get just a little bit different here by virtue of what it's like to be a halogen more than anything. And what I'm denoting here is with a bunch of dotted lines is essentially this bromine coordinates all at once to this. So we don't have a Markovnikov, anti-Markovnikov situation here. We've got a bromine that is essentially partially positive. And this species right here in your textbook is going to be partially negative. And so at this point in time, we just get breakage. I'm sorry, I have these backwards. Partially negative, partially positive here. We have breakage of this bromine away to give us something that will make just a little bit more sense, which is a bromine that's kind of partially attached to both of those carbons at the same time, and a bromine that is now negative. Hey, here we again, even though we had to go through this one kind of weird step, if we take out the weirdness, we now have a nucleophile, and we've got a position where both of these carbons right here are partially positive. One is less sterically hindered. Right here, and so you get breakage of this bond to form the bromine added across that double bond. And to close out lecture for the day, do we have to look at the stereochemistry of this product that could potentially be formed? And this is really where the danger in these reactions come from, of is acknowledging when in fact other products are formed. What I want to do first is just calm your nerves. If in an examination you are able to deduce that this is the product from this reaction without the stereochemistry, you will get at least half credit, if not 2/3 credit for that reaction. Being able to do the next step, which is fully write down and acknowledge all the products that are formed, if you can do that, that'll get you the other half to a quarter of a point. What I just want you to know is this does not sink your ship if you get to here. This to me is getting to this product right here is solid B understanding. I have a nucleophile. I have this species which can behave as an electrophile, and it adds two bromines. That is solid B understanding, and I will reward that with B understanding. Great, but just acknowledge that, oh crap, this chiral, this chiral. And so when we look at the products that are actually could be formed from this reaction, we have to look at what happens to each of these bromines in the products, depending upon which way the bromines were added when the bonds were formed and broken. What I'm illustrating is how complex these reactions can be. This is the total number of products that would be formed from this reaction. And these have enantiomeric and diastereomeric relationships that you may have remembered from OChem 1. It's not something I want to get into, but I will just tell you a quick story about this, and then we'll close up lecture. Why is organic chemistry such a difficult topic, and why does it have so many consequences? Well, right here, you just saw the formation of 4 possible products from one reaction. Let's say that just one of those products is the next cure for cancer. You're going to have to find and make that compound and isolate that one compound from the other 3 compounds. And so that becomes really difficult to do. That's purification. Once you've isolated this one compound, you have to pay $4 billion to prove that this is the next cancer drug. That's pretty much worth it because you're going to recoup that cost. These 3 other drugs, these 3 other molecules that were formed as possible products in your reaction synthesis, guess what you have to do there? You have to take all 3 of those compounds and get through at least phase 2 clinical trials at a cool $2 billion a piece. So $6 billion here, 4 more billion dollars here. That's $10 billion. And you have to prove with these 3 other compounds that if they existed, even in the tiniest amount, that it wouldn't kill you. Because if you have to synthesize the one you want, and these other three could persist, you have to prove that if they persisted, they didn't kill you. And fundamentally, that becomes insanely expensive. I'm not trying to justify what pharmaceutical companies do with pricing, but just know to get one drug all the way through to prove clinical trials to market, you typically have to take a few 10, 15-ish other molecules that were produced along the way and prove they don't kill you. And that all comes at the cost of the pharmaceutical company. Something to think about. I will hang out here until everybody logs off. If you have any questions or have any concerns, I will be posting the notes from today's lecture online for you immediately after this. I will be posting the chapter for those of you that are still having difficulty getting to the online textbook. I will post the text that will get us through Monday online as well. I'll photocopy that. And for those that want to, I will see you this evening at 8:30 to do some practice problems that pertain to this material. Get out, enjoy the day if it's nice for you. I have a 35-mile ride that I have to do for my Tour de France challenge. I will see you this evening. Have a great day.
Hey, I have a quick question, Dr. Shaw.
Yeah.
Um, so I know you're not a lab professor or anything, but right now I'm trying to work on trying to like open Topspin up, and it says I need like a license or a verification, and I have submitted a form for an academic license, and I still haven't got anything back from Topspin, and I don't really have access to a PC to download the other program.
Yeah, I'm not sure. I don't teach OChem 2 lab at all. I only teach OChem 1 lab. And so you might just want to reach out to your instructor for that one.
Okay, thank you. I appreciate it.
Yeah, I wish I could help more, but that's about all they let me know.
All right, thank you.
Yeah.